Hi everyone, let us solve few problems on Boolean Algebra from GATE examination. First question is, the K-map for a Boolean function is shown in figure. The number of essential prime implicants for this function is. So this problem is on K-map. So let us form the groups. See, there are no possibilities of grouping either 16 adjacent ones or 8 adjacent ones. So yes, there is one possibility of grouping 4 adjacent ones, right? And we can group these two ones, adjacent ones. We can group these two adjacent ones and these two adjacent ones. So we have total of 4 groups. So there is no single one left as ungrouped, so we need not check further. So we are asked to find the number of essential prime implicants. Prime implicants are all possible groups formed in K-map, and essential prime implicants are those groups which cover at least one minterm that cannot be covered by any other prime implicant. See, this one, and obviously 3 groups, and in this group. So all groups are prime implicants and all groups are essential prime implicants, which will appear in the final solution. So answer is 4. Let us go to next question. Since in this question, the Boolean expression for the truth table shown is, since all the options are in product of sum form, right? So let us construct K-map for 3 variables with max terms. Write max terms for this 0. Okay, so this is 0, 1, 2, 4, 5 and 7. Okay, so here it is 0 and 0, 2, then 4, 5 and 7. This is 0, 1, now let us form the groups. This is one group and second group is this, and third one is yes. Now this is A, this is A complement, this is B, C, B, C complement, B complement, C complement, B complement and C. So in product of sum form, we'll have For this group of 4, we have only B in common. Okay. For this group, we have A complement and C complement in common. So write that in product of sum form, A complement and C complement. Again, for this group, we have A in common and C in common. So A plus C. So we minimized this Boolean expression using K-map. So now you can verify your answer. So let us say see, any output expression is simply the sum of product representation of inputs that give an output of 1 or high. So let us verify. So write sum of product for this and this term. So we'll have A complement B C plus A B C complement. A A B C complement plus A complement B C. Yes. And let us simplify this. B A complement plus B C complement A plus C. B A complement A, that is 0. B A complement C, so A complement B C plus A B C complement plus B C complement C is again 0. So our answer is verified. Let us see the next question. The number of distinct Boolean expressions of 4 variables is. The number of Boolean expressions for n variable is 2 raised to the power 2 raised to the power n. So number of Boolean expressions for 4 variable would be 2 raised to the power 2 raised to the power 4, that is 2 raised to the power 16, that is 65,536. So D is the answer. Here A complement C complement A is the answer. Okay. Next question is the number of product terms in the minimized sum of product expression obtained through the following K-map is. So D denotes the don't care states. Don't care in K-map or truth table may be either ones or zeros. As long as we don't care what the output is for an input condition we never expect to see. So when forming group of cells, treat the don't care cell as either 1 or a 0. Yes? Or ignore the don't care. Only use them in a group if it simplifies the logic. See here. So let us form the group. Right? And see here we can left these don't care as unused because I don't see them in helping in minimization or simplification. So let us write the expression for the group. So f is equal to, say this is A, B, C, D. So A complement B complement, A complement B, AB complement AB. Okay, I wrote AB. So let us interchange this. AB here and CD here below. So C complement D complement, C complement D, C D complement and CD. Okay. Now write the sum of product expression. So this will be A. Okay, wait. For this group, for the largest group of 4, we have common B complement and D complement. So we have B complement and D complement, plus for this grouping, we have common, A is common and C is common, and also A, B complement and C. So A, B complement C. Okay, this is the final expression. So number of product terms in the minimized sum of product expression is 2. Yes. So let us see one example. Showing when there is the requirement to group the don't cares, and when there is no requirement to group or see. Let us have an example. A, B, C, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. So here, let us say we don't group don't care. Okay, let us change the color. Okay, now here I want to group this don't care. I want to include this don't care in the group. Okay, so now let us write sum of product for this. So for this we will have A, B complement and C, and for this we have A and C, right? So here output is 1 for input A complement B A B complement C, and for here, so this solution is the more complex solution since we did not use the don't care cells, right? Clear? So this is obviously less complex. So let us see the next problem. The Boolean function y is equal to ab plus cd is to be realized using only 2 input NAND gates. The minimum number of gates required is. So we have ab plus cd, ab plus cd. So since this is the question is asking NAND realization, so we can complement this 2 times. Now from De Morgan's law, we can write this as AB complement dot CD complement and whole complement. So now we have used only NAND gates. So we need only NAND gates in this from this expression. So let us show this through drawing the gates. One NAND gate for AB, 2 NAND gate for AB and CD, AB and CD. So now again one NAND gate is required for here output is AB complement and here CD complement and here AB complement, CD complement, whole complement. Okay, so now this expression can be implemented with 2 level NAND circuit, mean 3 NAND gates. So B is the answer. Okay. Similarly, if you had to realize A plus B and C plus D by using NOR gates. So again you can do what you could have done, A plus B, C plus D, double complement, again A plus B complement plus C plus D complement, whole complement. So again you will require 3 NOR gates, AB, CD, right? So if you had only 2 inputs, for 2 input, okay, for you, if you have to realize OR gate using NAND gate, OR gate using NAND gate. So you can write this as A into A to plus B dot B. Again this is of the form AB plus CD, like this. So again you will require 3 NAND gate. Let me show how. So you will have to common input to both the 2 input terminals. Okay, again for B, and then A. Here it will be, output will be A dot A dot B complement, whole complement, right? Again, if here it was 4 inputs, now what if you have 6 input? If you have to find AB plus CD plus EF, realize this with the minimum number of NAND gates required. So for these four input you just saw, we required 3 gates, 3 number of NAND gates. So let us say output of this is as x. So x plus EF again you can write this as x plus EF, again 3 NAND gates. So 3 NAND gates for this and 3 NAND gate for this. So total of 6 NAND gate required for 6 input. Yes. So similarly you can show number of NAND gates and NOR gates required for 2 inputs, 3 2 inputs, 4 inputs, 6 inputs. So you must remember this table. NAND, NOR means number of NAND gate required, number of NOR gate required. For NOT gate, AND gate, OR gate, XOR, XNOR. Yes. So to realize NOT gate using NAND gate, we require only one NAND gate and one NOR gate. To realize AND gate using NAND gate, we require 2 NAND gate and 3 NOR gates. To realize OR gate using NAND gates, we need 3 NAND gates and 2 NOR gates. So and to realize XOR gate using NAND gate, we need 4 NAND gate and 5 NOR gate. To realize XNOR gate, we need 5 NAND gate and 4 NOR gate. That is why NAND gate and NOR gates are universal gates. So let me show how I remembered this. So remember this NaO. Wait. NaO XOR and XNOR and 1, 2, 3, 4, 5. Similarly here write 1, 2, 3, 4 and 5. So remember this table, minimum number of NAND gate required and NOR gates required for every gates. Okay, let us go to the next problem. In the sum of product function, the prime implicants are. So we are given sum of product, min terms. Let us construct K-map. X, Y, Z 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. We have 2, 3, 4, 5. So 0, 1, 0, 1, 2, 3. So 2, 3, 4, 5, 6, 7, 4, 5. So let us form the group. Let us combine these two cells and these two ones. Yes, so there are 2 prime implicants and they are X and Y complement plus second product term is X complement and Y. Okay, so answer is A. Let us go to the next problem. For an n variable Boolean function, maximum number of prime implicants is. See, for two variable K map, we have 4 cells. Let us assume each cell has 1. To get maximum number of prime implicants, combine adjacent cells and you will get maximum number of prime implicants by combining least number of cells, which is 2 number of cells at a time. Okay, so here there will be 2 prime implicants, right? Similarly, if we have 3 variables, so for 3 variables K map, we will have 8 cells, 8 number of cells. So assume that each cell has 1. And to get maximum number of prime implicants, you will get by combining least number of cells, which is 2 again. So there are 4 prime implicants here. See, number of prime implicants is nothing but number of product terms you are getting. So again, for 4 variable K map, if each cell has 1, start combining 2 cells, 2 adjacent cells. So there will be 8 number of prime implicants or 8 number of product terms. So you see, you can write this as 2 power 2 by 2. You can write 4 as 2 power 3 by 2 again. Okay. And for 8, you can write this as 2 power 4 by 2. Yes, where these power are the number of variables. So you can sum this up as 2 power n by 2, which is 2 power n minus 1. Clear? So answer is D. Okay, let's move to the next question. Here, a function f defined by 3 Boolean variables a, b, c when expressed as sum of product is given by where a complement, b complement and c complements are the complements of respective variables. The product of sum form of the function f is. So we are given sum of products form and we have to find the product of sum form. So we know that product of sum form is not equal to complement of sum of product form. So first of all, what you can do is we have to find product of sum form. So product of sum form is equal to, first take the complement of the function and then sum of product of complement of the function, again take complement of the function, then you will get product of sum form, right? So here A complement B complement C complement A is 0. A complement B C complement is 2. And this is 4. So we need to find 1, 3, 5, 6 and 7. Yes? Okay. So F complement is A complement B complement C plus A complement B C plus A B complement C plus A B C complement plus A B C. So this is complement of function f. Now again taking the complement of this function, the new function. Okay, so take complement, whole complement. You will take whole complement, then you will get A plus B plus C complement, A plus B complement plus C complement, A complement plus B plus C complement, A complement plus B complement C plus C, A complement plus B complement plus C complement. Verify this again. Yes. Right. So answer is C. Next, go to the next question. If the functions w, x, y, z are as follows, so find the correct option. So let us first minimize these expressions. So for w, we can write p complement q plus r complement into r plus s. R plus s. X is equal to PQ R complement S complement. Okay, so you can take Q complement R complement S complement common here, Q complement R complement S complement, then P plus P complement. So again this is one P plus P complement. So now again you can take R complement and S complement common. So you will have PQ plus Q complement. Again you can write this as PQ Q complement plus Q and Q complement plus P. So this is one. So now R complement S complement Q complement plus P, which is P R complement S complement plus Q complement R complement and S complement. Again, let's simplify Y. So see, here you can take Q complement out, Q complement common, and then P plus P complement, which is 1. So we are left with only PR plus Q complement. Let us rewrite Y as RS plus PR plus PQ complement plus P complement Q complement, or you can rewrite this as Q complement common, take out Q complement common, and P plus P complement yes. So we have RS plus PR plus Q complement. Again, RS plus P complement plus R complement and Q complement. So you can remove this complement. Yes. So RS plus P complement Q plus R complement Q. Then let's simplify Z. So Z is equal to R plus S plus PQ plus P complement Q complement R complement plus PQ complement S complement whole complement. Again R plus S plus P, take P common, so Q plus Q complement S complement and P complement Q complement R complement. Again R plus S plus P, again Q plus Q complement times into Q plus S complement. So Q plus Q complement will be 1. We will have Q plus S complement plus P complement Q complement R complement. Yes, R plus S. Now let's simplify this complement part. So P complement plus Q complement S and P complement plus Q complement plus R complement. So P plus Q plus R. Again R plus S plus P complement 0, P complement Q P complement R, Q complement SP, P Q complement S, this is 0, Q complement Q, R Q complement S. Now take R common from here and here, so 1 plus P complement, and take S common from this and this, so S out, so P Q complement plus Q complement R plus 1 and plus P complement Q. So this is 1, 1 plus anything is 1. So this is 1, 2. So R plus S plus P complement Q. Minimized. So we have minimized W, X, Y, Z. So now let's see W and Z. Notice W, so this is R plus S plus P complement Q. So notice W and Z. W and Z, they are same. So W is equal to Z first, and X is equal to X and so only A and C could be true. B and D is wrong because W is Z is there in A and C. So let's check X, whether X is equal to Z complement and X is equal to Y. So let's see X. X is P R complement S complement plus Q complement R complement S complement, and Y is this. So these expressions are not equal. So X is not equal to Y. Now let's check whether X is equal to Z complement. So X is this and Z is this. Let us complement this. R plus S plus P complement Q. R plus S plus P complement Q. So now you can write this as R plus S complement. Yes. Again R complement S complement P plus Q complement. Now R complement S complement P plus Q complement R complement S complement. So this is true. X is equal to Z complement. Let's go to the next question. A Boolean function f of two variables x and y is defined as follows. Assuming complements of x and y are not available, a minimum cost solution for realizing f using only two input NOR gates and two input OR gates, each having unit cost, would have a total cost. So here, let us construct the truth table x, y, f. So we are given 0, 0, 0, 1, 1, 1 as 1. So 1, 1 and 1. And f10 is 0. So let us minimize this with the help of K-map. Since there are two variables, so we will have 4 cells. Okay, so 0 as 1 and 1, 1. Now combine these two cells and these two ones. So from here, from this grouping we can write x complement plus, From this grouping we can write y. So we have f as minimized function as x complement plus y. Now we have to use 2 input NOR gates and 2 input OR gates. So condition given as variables are available only in uncomplementary form. Complements x, y are not available. So to construct x, to get x complement, let us use NOR gate here, because NOR truth table is yes. So if both inputs are same, the NOR gate will complement the input. So if x, y are same, output will be the complement. So yes, we'll get x complement from NOR gate. Yes, the output will be x complement. And since we have plus here, so we can use or 2 input OR gate. So one output is x complement and one output is y. Okay, so we have the answer x complement plus y. So 2 gates are required. So 2 gates are required and each having 1 unit cost, 1 unit. So total cost will be 2 units. Okay, let's go to the next question. The point P in the following figure is stuck at 1. Okay, so here P is stuck at 1, the output F will be. So P is 1, these are NAND gates. So we have only NAND gates. So let's draw the truth table for NAND gates. So here all inputs are same. So this will be B complement. Here C complement. Again here B, C complement, whole complement. Here B again. But this output is, here P is, this point is stuck at 1. So this is 1. Again B, C complement, whole complement. And again complement, then BC complement. So if this is stuck at 1, so both are 1, then output will be 0. Then even if at least one input is 0, then output is 1. So output is 1 here. So one output is 1, one output is A. So here our answer will be A complement. And again after a NAND gate, you will have A as the result. A complement which is A. So you see that this part is not affecting the final output. Yes, the answer will be A. Let's move on to the next question, next problem. If x is equal to 1 in the logic equation, then x is 1 in here. So if x is 1, x complement is 0. So let us put the value x as 1. See, 1 plus anything is 1. So this is equal to 1. So 1 into x complement is 0. So z complement x is 1, 1 plus y. So 1. So is equal to 1. Z complement is equal to 1. That means z is 0. I repeat, since x is 1, 1 plus anything is 1. So this reduces to 1. And here x complement is 0. So plus z complement x is 1, 1 plus y, which is 1 again. So we are reduced, the equation is reduced to z complement is equal to 1. That is z, that gives z is equal to 0. So D is the answer. Next question. Consider the Boolean function. Which one of the following is the complete set of essential prime implicants? Okay. So you see here, since we have 4 variables, but here 2 variables are missing in each product term. So let us multiply x plus x complement and z plus z complement. Here since x plus x complement is 1, z plus z complement is 1, is not going to affect this value, this product term. So let us multiply here, and this with w plus w complement and z plus z complement. Here all variables are present. Here z is missing, so multiply this by z plus z complement. Here w and y are missing, so w plus w complement and y plus y complement, and here also w is missing. So let us do that. So wy x plus x complement and z plus z complement. Similarly xy w plus w complement, z plus z complement, plus wx w complement x y z plus w complement x complement y z plus z complement, plus xz w plus w complement and y plus y complement, plus x complement y complement z complement w plus w complement. So this is wxyz and wy x complement wyx z complement, again wy x complement z, wy x complement z complement, again wxyz, which is redundant, so which is already present, so leave that. So xy wz complement, okay, xy wz complement, which is again redundant, so leave that. xy w complement z, xy w complement z complement, again w complement x y z, so which is present, so leave that. Next w complement x complement, Y, Z. Y, Z. W complement, X complement. Y, Z complement. Yes. Again. X, Z, W, Y, which is redundant. X, Z, W, Y complement. Plus X, Z, W complement, Y complement. Plus X complement, Y complement, Z complement, W. Plus W complement, X complement, Y complement, Z complement. Okay. So now we can, since we have already arranged, so let's rearrange this as summation of minterms. This is 0, 0. This is here it is Z complement, so this is 8, this is 5, and this is 13, this is 2, this is 3, and this is 6. This is 7. Again this is 13. Sorry, 8, 4, 12. Wait. 10. This is 11. And this is 14. And yes, this is 15. So let us draw the K-map, construct the K-map consisting of 16 cells since we have 4 variables. So we have 4 variables. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So we have 1 here, 2, 3, 5, 6, 7, 2, 3, 5, 6, 7, 8, 10, 11, 8, 10, 11, 13, 14, 15. Okay, now let's form the groups. So we have one group here formed by these 4 cells. Again, these 4 cells can be grouped together. And okay, we have 8, we can group 8 cells here. Here 2, 4, 6, 8. We can group in the power of 2. So we can group 8 cells. And now these are left. So 1 cell, 1, and group of 4 cells. So let's say this is Wx, this is Yz. So this group will give us, from this group we have Xz. From this group of 8 we have only Y, and from this group we have X complement, Z complement. So essential prime implicants are Y, Xz, X complement, Z complement. That is D. Right? A function of Boolean variables x, y, z is expressed in terms of mid-terms as which one of the product of sums given below is equal to the function f of x, y, z. So we are given min terms or sum of product. So we have to find product of sum. So we have 1, 2, 5, 6, 7. So let us write min terms for 0, 3, 4. Yes. So for 0 it is x complement, y complement, z complement plus 3 will be x, y, z plus 4 will be yes. Now take complement. So we'll have x plus y plus z. This as x plus y complement plus z complement, and this as x complement plus y plus z. So the answer is B. Okay. So next question is, following is the K-map of a Boolean function of 5 variables P, Q, R, S and X. The minimum sum of product expression for the function is. So we are given x for x is equal to 0 and for x is equal to 1. So we can group here for these two cells and these two cells, 4 cells together, and these two cells and these two cells. So this will give S and Q complement, S Q complement, and this will give S complement and Q. S complement and Q. So here x is 1, so take this as x, and since x is logic 0, so x complement. So this is the answer. Q complement S, X complement Q, S complement X. So B is the answer. For the circuit shown below, the output F is given by. So this is the XOR gate. Truth table for XOR gate will be yes. So here both inputs are same. So for the same input, output is 0. So here this is 0. Again 1 is 0 and 1 is X. So if one input is 0, so we will have X here if one input is 0 and one input is x, so output is x. Again x we have same, so 0, so output is 0. See, if this is x can be anything 0 or 1, and one input is fixed as 0. So see, output is for 0 0 0 1 0 1, so output is x only. Okay, let's proceed. Minimum number of 2 input NAND gates required to implement the function f is equal to x complement plus y complement z plus w. Okay, let us minimize this first. In order, we have to, for NAND gate we have to keep that in mind, that for NAND gate we have to simplify this. So one NAND gate here. Okay, now z plus, we can write x complement plus y complement as x y complement, then x y complement in times z plus x y complement complement w. Again taking double complement, so we have x y complement z, x y complement w, complement complement, again a complement. Yes, so how many NAND gates we require? One for xy, one for xy complement, second for xy complement z for this, and third for this, and fourth for this. So we need total of 4 NAND gates. Okay, one for xy complement, four NAND gates, one for xy complement, second for one for xy complement z whole complement, one for xy complement whole complement w, and one for xy yes, so total of 4 NAND gates we require. The minimum number of NAND gates required to implement the Boolean function is equal to, okay, so let us first simplify this. Yes, we can do that. Take a out, 1 plus b complement plus b complement c. So this is a again, because this is 1. So we don't need any number of gates here. Even single NAND gate is not required to implement this function. So 0. Next, if the input to the digital circuit consisting of a cascade of 20 XOR gates is x, then the output y is equal to. So there are 20 XOR. One input to each XOR gate is x. So let us recall the truth table for XOR gate. So which is 1 if the inputs are different, and 0 if the inputs are same. Yes, so for this XOR gate we have 1 and x. Output will be x complement, and again for this XOR gate we have one x complement and x as input, so output will be 1. Again for the third XOR gate we have 1 and x, so again output will be x complement. So even gate output is 1 and odd gate output is x complement. So for 20 XOR gates we have output 1. 20 is even and output is 1. So answer is B. Yes. Let us proceed. The output Y in the circuit below is always 1 when, okay. So output here for this NAND gate is P, PQ, P and Q complement, and here this is Q and R complement, and for this it is P and R complement. So PQ complement and QR complement. Whole complement, so which will be PQ plus QR. Okay, so we can write this as PQ plus QR. So again here the output is same. So here output will be PQ plus QR complement, and here PR complement. So output Y will be PQ plus QR complement and PR complement whole complement. So let us rewrite this as PQ complement plus QR complement and plus PR complement. Yes. So PQ plus QR plus PR. The output Y should always be 1. So this should be 1. So any of these three products, if any of these three products are 1, then output is 1. At least one of these product term is 1, then output is 1. Say if PQ is 1 or if QR is 1 or if PR is 1. So for PQ to be 1, P is 1 and Q is 1, both are 1. For QR to be 1, Q and R both are 1. For PR to be 1, P and R both are 1. So any of these three products, if it is 1, then output is 1. So at least any of these three products. You can say we can have PQ as 1 or PQ plus QR as 1 or and PR is 0 or PQ plus PR is equal to 1 or all of them are 1. So at least 2 inputs are 1. So this output Y is 1 for at least 2 input as 1. Means 2 or more of the input PQR are 1. So B is the answer. Next. Okay, a bulb in a staircase has 2 switches. One switch being at the ground floor and the other one at the first floor. The bulb can be turned on and also can be turned off by any one of the switches irrespective of the state of the other switch. The logic of the switching of the bulb resembles. So let us say we have S1 in the ground floor and S2 in the first floor. So bulb status can be toggled by charging any switch from 0 to 1 or 1 to 0. So let us see 0, 0, 0 means output. So bulb is off. Let's say if S2 is 1, so 1 output should be on. Again 1, 0, yes, again on, and if both are 1, then bulb is off. So this truth table matches the truth table of XOR gate. So XOR gate is the answer. So next question. In the circuit shown, diodes D1, D2 and D3 are ideal and the inputs E1, E2, E3 are 0 volt for logic 0 and 10 volt for logic 1. What logic gate does the circuit represents? So see here, if E1, E2 and or E3 is equal to 0 volt, then the corresponding diode will be on because of that V0 will be 0. Yes, if any of the diode is on, then and if E1, E2, E3, E1 or E2 or E3 is 0 volt, then only diode is on and then V0 will be 0 volt. But when all the diodes are off, that is when all of E1, E2, E3 is 10 volt, if all of them are 10 volt, then the current across the 1 kilo ohm resistor is 0 and V0 is 10 volt, which is logic 1. Yes, so this is similar to AND gate. When if all the input are 1, then only the output will be 1, else it is 0. So answer is AND gate. You can draw truth table this way. Zero zero 1 0 1 1 1 0 1 1 1. So output is 1 only when 0 it is logic 0. So when V0 is 0, when either of E1, E2, E3 is 0. So output is 0, logic 0 when 0 0 0 0, right? And so when all of the 3 E1, E2, E3 is 10 volt or so then here it is 10 volt, diodes are off and no current flowing through this resistor. So then only we have 1 as the output, logic 1 at the output. Yes, so this truth table is of that of 3 input AND gate. In the figure, the LED, okay, 4 options are given. So for this LED to emit light, this diode should be forward biased. Okay, so this will emit light only if, see, this is 5 volt, so this should be 0 volt. Okay, so if this is 0, then only this LED will emit light. So see here, so okay, this is NAND gate. So when is NAND gate output 0? Yes, only when both inputs are 1. So for this to be 0, this should be 1 and this should be 1. And for this should be 1, for this to be 1, both inputs should be 1, because this is an AND gate, both inputs should be 1. But see, either this is connected to S2 or this is connected to S1. So either this is connected to S2 or either this is connected to S1. So one of the input is always 0. Yes, one of the input is always 0. So this will never be 1. This will never be 1. This will be 0. So this NAND output never becomes 0. Hence, LED does not emit light irrespective of the switch position. So answer is D. Okay. The gates G1, G and G2 in the figure have propagation delays of 10 nanoseconds and 20 nanoseconds respectively. If the input V1 makes an abrupt change from logic 0 to 1 at time t is equal to t0, then the output waveform V0 is. So propagation delay of NOR gate is 10 nanosecond and propagation delay of NOR gate is 10 nanosecond, propagation delay of XOR gate is 20 nanosecond. So total delay of 30 nanoseconds. Now let's say we have Vi as, okay, now here output is Vi complement. Yes, output is Vi complement. So, and since there is a delay of 10 nanoseconds, so at T0, here this is T0, so at T0 there is a change, but since there is a delay, so it will delay, there is a delay of 10 nanosecond and then output will change, which is Vi complement. Yes, again here output is, so Vi, there is Vi complement and there is Vi. This is output at G1 and output at G2. So output at G2, so here this is X, output at G2 is affected by Vi, depends upon Vi and output at G1. So at this point, say output at T0 plus, and here output at T0 plus, G2 output at G2 tends to change, but since there is a delay of 20 nanoseconds, so there will be, so after T0, there will be delay of 20 nanoseconds, and then there will be a transition. Since both outputs are 1, so this is a XOR gate, so output will be 0. So there will be transition from 1 to 0 at after 20 nanoseconds. So if this is T0, this is T0 plus 10, and this is T0 plus 10, and this is T0 plus 20. Yes. Then again at here, after T0 plus 10 nanoseconds, so there is a change in the output at G1, and Vi is 1, and output at G1 is 0. So since output at G2 is responding to both input, responding to change at output at G1 and this Vi, so since there is a delay of 10 nanoseconds in the input side, so at output there is a delay of 20 nanoseconds, so total of 30 nanoseconds. So at means let us redraw output at G2. So at T0 plus 30 seconds, there will be a transition. Since one input to XOR gate is 1 and one input is 0. So at 10, at 20, T0 plus 20, there is a transition, and again at 30 there will be a transition. Yes. So answer will be C here. C. The best way to solve such kind of problems is through timing diagrams. The delay in the circuit can be caused due to the gates or due to buffers or inverter. So you should take it step by step. So based on the given input, deduce the output without considering the time delays. Okay, let us redraw. So Vi is okay, T0. So NOR output without delay, let's say NOR output without delay, right? So see, output is Vi complement here. So if there is no delay, there will be instant transition at T0. But if there is a delay, with delay, output will be shifted. Okay, shifted 10 nanoseconds towards right. Right? So here 10 nanoseconds with delay. Now XOR output without delay will be if there is no delay, then see here, consider this. So there is one here and there is one here. So that means when both inputs are 1, then XOR output is 0. So output will be 0, and then wait, output is 0. Then here input is 1 and output is 0. So output is again again 1, because there are different inputs, so output of XOR is 1. Yes, so this was XOR without delay, and XOR with delay, so there is no space. So let us redraw here. So with delay, how there is delay of 20 nanoseconds. So this will be shifted towards right after 20 nanoseconds. So let us redraw this. So with delay will be okay, earlier it was okay. So shifted version will be, now with delay we will have 20 nanoseconds delay due to XOR. Yes. So this will be 10, 10 and 20. Okay. So here total delay is 20 nanoseconds. So through timing diagram it is easy to find the exact delay corresponding to each gates. So answer is C. Let's go to the next problem. A 3-input majority gate is defined by the logic AB plus BC plus CA. Which one of the following gates is represented by the function? Okay. So let us find M of ABC complement. So complement, so which is AB complement, BC complement and CA complement. Again A complement plus B complement, B complement plus C complement, C complement plus A complement. So if you expand, so you will get A complement B complement, A complement C complement, and B complement C complement. Yes. Again Let's find MABC complement. So ABC complement, that is BC complement plus C complement A. So AB plus BC complement plus C complement A. Now we have to find function of this, this and C. So put this in place of A and this in place of B and C is C. So we have B complement C complement plus A complement B complement plus A complement C complement and AB plus BC complement plus C complement A. So A B. So we are actually multiplying this and this plus BC. So B and C, then C and A. Okay. So again plus AB plus B complement C complement plus C complement A times C plus B complement C complement plus A complement B complement plus A complement C complement C. Let us simplify this. Okay. So after simplification, you will get A B complement C complement plus A complement B C complement plus A B C plus A complement B complement C. So take out C common, C complement. So A B complement plus A B A complement B. Yes. From these two. Again plus take out C common. So AB plus A complement B complement. So which is, you can write as the minterm as 1247 or it is A XOR B XOR C. This output is A XOR B XOR C. So that means this is a 3 input XOR gate. So B is the answer. Yes. A universal gate is a gate by which every other gate can be realized, and or not are basic gates, and NAND and NOR are universal gate because NAND and NOR gate are universal gates. So if we can get a NAND or NOR gate expression from any of these gates, then we can say that gate is universal. So gate 1 is OR gate, so and gate 2 is AND gate. So these two are basic gates. So let's see gate number 3. So which can be written as yes. or x complement plus y complement. So gate number 3, we are getting a NAND gate expression. So gate number 3 is a universal gate. Yes? Okay, clear? Which one of the following is equivalent to AND OR realization? We just saw such example, one example, AB plus CD. We realized this AND OR gates with NAND realization. So A, B, C, D. Yes. So we require 3 NAND gate to realize this AND OR realization. Okay. Similarly, for A, B, C, D, E, F, we require 6 NAND gate. So we just saw this, that NAND realization is equivalent to AND OR realization. So answer C is the correct answer. Next is the input waveform Vi and the output waveform V0 of a schematic NAND are shown in the given figures. The duty cycle of the output waveform will be. So we have to find duty cycle. Duty cycle is T on by time period. Time period or T on by T on plus T off into 100%. So now we are not given time. So here we need to find T1 by T2 because T2 is the time period. So we are not given time. So and from the data given we can find slope here, and we can find slope since we have been given the voltage level, and so let us find the slope of this. So 1.7 minus 0.4 by T1. So slope is 1.7 minus 0.4 is equal to T1. And for this slope is 2.2 minus 1.7 by T2 minus T1. Slope is same in both the case. So just equate and then T2 minus T1 by T1 is equal to 0.5 by 1.3. This is T2 by T1 minus 1 is equal to 0.5 by 1.3. So if this comes here plus 1, so we have T2 by T1 as 1.8 by 1.3 or T1 by T2 as 1.3 by 1.8, and so duty cycle will be 21 into T1 by T2 into 100%, which is 1.3 by 1.8 into 100 is equal to 72.2%. So C is the answer. Okay, that's all for today. So we will learn combinational circuits in the next lecture. So till then, keep preparing. Thank you.